Subject: Signals and Systems. Topic is Introduction of a Signals and the different type of signals. Lecture delivered by Indranil Sarkar. Introduction to signals. A signal is the function of one or more independent variables that carry some information to represent a physical phenomenon. As an example, ECG, EEG. There are two types of signals: continuous time signals, discrete time signals. Continuous time signals. Signals that has a value for all points in time. Function of time, written as xt because the signal x is a function of time. Commonly found in the physical world, as example, human speech, displayed graphically as a line. Suppose this is the time axis and this is the signal xt, and some signal is plotted over here. Discrete time signals. Signals that has a value for one only specific points in time, typically formed by sampling a continuous time signal, taking the value of the original waveform at specific intervals in time. Function of the sample's value n, written as x n, often called a sequence. Commonly found in digital world, as example web file or MP3. Displayed graphically as individual values called a stem plot. Here in the horizontal axis we are taking the sequence n, represented as a n, and these are the 1, 2, 3, 4, these are the sample numbers, and the signal is represented in vertical axis xn. Here it is the examples of continuous time signal versus discrete time signals. In the left side we see that this is a continuous time signal xt. In every point there is a output. And in the right side we see this is the sampled continuous time signal, which is represented as a sequence n, and the signal is xn. Here it is the sampled value. Sampling. Discrete time signals are often obtained by sampling continuous time signal. Here xt goes through the converter which converts from continuous time to discrete time and represented as an xn, which is equal to xt when small t is equal to n capital T, and capital T is the time period, and which is also represented as a x bracket n capital T. And below are the left side is the continuous time signal and right side is the sampled continuous time signal. Elementary signal. First, unit step signal, which is represented as a ut. Ut is equal to 1 for t greater than equal to 0 and 0 for t less than 0. Now in the figure we see that in the right hand side portion, in the positive axis, we see that there is the value 1, which is represented ut is equal to 1 for all values. That means t greater than 0, there is a value which is fixed value, and that is 1. And in the negative side, in the negative axis, we see that ut is equal to 0 for t less than 0. Same way, for sample signal, we can write un equal to 1 for n greater than equal to 0 and 0 for n less than 0. Unit ramp function. The figure shows the ramp function. This is a straight line which is in 45-degree angles. Here ramp t is equal to t for t greater than 0 and 0 for t less than equal to 0, which is represented as the integration of minus infinity to t u lambda d lambda is equal to t ut. The unit ramp function is the integral of the unit step function. It is called the unit ramp function because for positive t, its slope is 1 amplitude unit per time. Unit impulse function. As a approaches 0, gt approaches a unit step and g dash t approaches a unit impulse. Here in the left side we see this is the signal GT, which is the ramp signal, started from minus a by 2 to the plus a by 2, and it is in slope and its height is 1. Now in the right side we see that this is G dash T, which is the unit impulse. Here it is the pulse signal starting from minus a by 2 to plus a by 2, but its height becomes 1 by a. That means here we are representing the functions that approach unit step and unit impulse. So unit impulse function is the derivative of the unit step function, or unit step is the integral of the unit impulse function. Representation of impulse function. The area under an impulse is called its strength or weight. It is represented graphically by a vertical arrow. An impulse with a strength of 1 is called a unit impulse. We know that for unit impulse the value is del t is equal to 1 when t equal to 0. That means here the signal is represented at t equal to 0, the value is 1, which is marked as an arrow represented in the left side, and it is the representation of unit impulse, and it is also called del function. In the right side we see that this is the amplitude 5 and it is shifted by 1. The signal is 5 del t minus 1. We know the condition del t is equal to 1 when t equal to 0. That means here del t equal to 1 when the value of t is equal to 1, then it becomes del t minus 1 equal to becomes 0. At del 0 we will get the value 1. So the signal is shifted to 1 and the amplitude is 5. That is why it is written as 5 del t minus 1. It is the shifted impulse of amplitude 5. Properties of impulse function. First, the sampling property, which is represented as integration of minus infinity to plus infinity gt del t minus t0 dt. When we will get the signal? Del t is equal to 1 when t equal to 0. Here when the value of t is equal to t0, then only there will be a value of 1 for del t minus t0. So the signal becomes here gt0. Next, the scaling property. Del at minus t0 is equal to 1 by mod a del t minus t0. Third is the replication property. Gt into dt is equal to gt. That means when the signal is combined or multiplied with a impulse function, the same function comes out. Unit impulse train. The unit impulse train is a sum of infinitely uniformly spaced impulses and is given by del capital T bracket n small t is equal to summation of n is equal to minus infinity to plus infinity del t minus n capital T. Here n is an integer and capital T is the time period. In the below figure it is represented the signal. Sinusoidal and exponential signals. Sinusoids and exponentials are important in signals and system analysis because they arise naturally in the solutions of the differential equations. Sinusoidal signals can expressed in either of two ways. Cyclic frequency from minus a sine 2 pi f0 t is equal to a sine 2 pi by capital T0 into t. Radian frequency from minus a sine omega 0 t. Omega 0 is equal to 2 pi f0 is equal to 2 pi by t0 because f0 is equal to 1 by t0, and t0 is the time period of the sinusoidal wave. Now xt is equal to a sine 2 pi f0 t plus theta is the sinusoidal signal, which is also represented as a sine omega 0 t plus theta. xt is equal to a e to the power at is the real exponential signal, and a e to the j omega t is equal to a cos omega 0 t plus j sin omega 0 t, which is the complex exponential signal. Here theta is the phase of sinusoidal wave, a is the amplitude of a sinusoidal or exponential signal, f0 is the fundamental cyclic frequency of sinusoidal signal, omega 0 is the radian frequency. Real exponential signals and damped sinusoidals. Here it is represented in the left side in the top corner. Xt is equal to e to the power minus alpha t or minus at. That means this is the decaying exponential signal which is in the positive side of the axis. In the right hand side we see that the signal is xt e to the power alpha t. Here the signal is also a decaying signal, but in the opposite direction or in the negative axis, and we can see that here it is written as rising exponential signal. That means in the left side we see that this is the decaying exponential signal, and in the right side we see that this is the rising exponential signal. Below there are also two types of signal for r less than 0. This is the decaying sinusoidal signal, and in the right side this is the growing sinusoidal signal, and represented as e to the power rt cos omega 0 t plus theta. And the signal is represented as xn is equal to e to the power n. Signum function, which is written as sgnt. The criteria is sgnt is equal to 1 for t greater than 0, 0 for t equal to 0, and minus 1 for t less than 0. And it can be represented as 2ut minus 1. In the below figure, it is represented as the signum function, where we see that when t greater than 0 there is a value of 1 which is uniform, and for t less than 0 there is a also value minus 1 which is also uniform. But at t equal to 0 there is no value. That means at t equal to 0 the value of signum function is 0. The signum function is closely related to the unit step function. Rectangular pulse or gate function. Rectangular pulse del at is equal to 1 by a. The criteria is mod t less than a by 2 and 0 for mod t greater than a by 2. Here the signal is represented, that is the pulse signal, and that is the rectangular pulse. It continues from minus a by 2 to plus a by 2, and its amplitude is 1 by a and represented as del at. The unit triangle function. A triangular impulse whose height and area are both 1 but its base width is not is called unit triangle function. The unit triangle is related to the unit rectangle through an operation called convolution, which is represented over here. The tri t, which is represented from minus 1 to plus 1. In the both side we see that this is the ramp function in the upper side, and in the right side this is in the lower side. That means this is the two type of ramp function. One is in the right path and one in the left path, and its amplitude is 1. Sinc function. Sinc t is equal to sin pi t by pi t, which is represented over here in this way. Sinc t, at t equal to 0 we will get the value 1, and others are the harmonics.